Okay, today we're going to continue to look at counting problems. And first off, a little explanation as to why we do counting problems. And it's all really based around computing the probability of different events. Anytime we want to look at the probability of an event, we have to know a couple of things. First off, we have to know the number of outcomes that we want. If we're looking at how many ways we can do something, the ways that it actually came out doing what we wanted it to do would be the numerator of our probability computation. And then, of course, you have to know the number of outcomes possible, meaning all the possible ways that this event could go. And when we're looking at figuring that out, a lot of times if we have multiple events or we're selecting multiple items out of a group or something to that effect, we have to use our counting rules. They come into play. And what we're going to focus our look at today is on the permutation rule and the combination rule. And we use these anytime we're going to get a set number of items selected from a group of items. Okay, we may have 20 items and we're going to pick out 5 of them. We may have 100 items, we're going to pick out 63 of them. It doesn't matter. But if we have a group of items and we're going to select a set number of items out of that, and we want to see how many different ways that can go, we're going to result to looking at the permutation rule or the combination rule. Now, in doing this, there's some major similarities between these two, and you can see the formulas down here at the bottom. As we look at these, we can see that they're very similar to one another, and likewise, they're very similar in the type of problem that we would use them in. So it's very important that we can distinguish between the two, but the main giveaway is we should ask ourselves if the order that the items are selected in matters. Is there going to be a difference between the first item selected and the second or third item selected? Are they going to be treated differently? Is something different going to happen for each one? Or are they all going to be the same? And we'll look at some examples where we're talking about that a little bit more, but if they're all going to be different from one another based on the order they're picked in, we would use the permutation rule. Now, the permutation rule is we take the total number of items that we have, we use the factorial of that value, and then we divide that by the factorial of that total number of items minus the amount that we're picking out. We'll look at some examples where we use that, and we'll also look at some examples where we use the combination rule. Well, the combination rule is for when the order does not matter. If we ask that question, does the order matter in which these items get picked, and we say no, then we're going to use the combination rule. And the only difference between the combination rule is that we get this one extra value that we have to divide by, and that's the number of items selected factorial. And that ends up making your values for the combination rule smaller in value than we would get for the permutation rule. The permutation rule values are going to be larger in value, or larger in value than we get from what we get from the combination rule. And it's just because we're dividing by that additional value down there, which reduces the number of occurrences down. And with that said, let's take a moment and let's look at some examples here and talk about how we use these actual formulas. Our first example talks about a manufacturer company that is looking at 12 different locations to place buildings that they're going to be using. They're going to build 3. They're going to build 3 buildings, and they're looking at 12 different construction sites on which to put those 3 different buildings. The first place that's picked is going to be the location of the sales offices. The second site that's selected will be the research and development headquarters. And the third site selected will be it's going to house the administrative offices, your managers and your CEOs and all of that stuff. So how many possible ways can the company select the land sites? Well, we're going to pick 3, and the first thing we're going to ask ourselves is, does the order of selection matter? That's all we're going to ask ourselves in determining which one of these methods we're going to use. Well, as we read through, we see the first site selected is going to be the sales offices. The second site is going to be the research and development. And the third site is going to house the administrative offices. So every place is going to be treated a little differently based on what order it gets picked in. So does the order matter? The answer is absolutely yes. Well, if the order matters, we should be using permutations. So we're going to use the permutation rule. Now the permutation rule again is the n number of items chosen through permutation r times. So we're going to choose, excuse me, I said that wrong. R number of items is going to be selected from n total. And we're going to see the permutations from those number of items. So that would be n factorial divided by n minus r factorial. Well, what is n here? N is the number of items that we're looking at total. So n is this 12 locations. And R represents the number of items that we're selecting out of the group. So in this case, R would be the 3 selections. Okay, so we have 12 total locations. We're going to select 3 out of those. So that said, let's go ahead and use these numbers in the formula. So we know that 12 items total, and we're selecting 3. Let me rewrite that. Would be 12 factorial divided by 12 minus 3 factorial. Now, factorials we've talked about a little bit in class. Remember what factorial means. It means that we are multiplying all of the integers greater than or less than or equal to that value. So in this case, I have 12 factorial over 9 factorial. That's going to be 12 times 11 times 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. And that takes a lot of time to say, but that's what it means. And then we look at 9 factorial. That's going to be 9, 8, 7, 6, 5, 4, 3, 2, and 1. And again, we're multiplying all those values. And we're going to divide 12 factorial by 9 factorial. Well, there is a shortcut here. If we look, we see that we have 9, 8, 7, 6, 5, 4, 3, 2, 1 on the bottom here, and we also have it on the top. And since we're dividing, we can just cancel those whole things out. So what that ends up leaving us with is the value that we get from 12 times 11 times 10. And of course that is 1,320. So there are 1,320 outcomes for selecting these different construction sites for the different buildings that we're going to put in. That's quite a bit. So we can see that permutations, by the fact that selecting site 1, site 2, and site 3 is a little bit different than selecting site 2, site 3, and site 1. You know, the order that they're picked in matters with what's going to go there. So when we have permutations, that's the situation that we're looking at. Let's look at another example. Another company is employing 17 people. At the most recent board meeting, it was determined that a $1,500 grant is going to be given to 10 of the employees. Those employees will be selected at random in order to pay for their additional training to advance their career. So they're going to give money to 10 of their 17 employees to advance their career, and those people are going to be selected at random. So how many different ways can the employees be selected to receive this bonus to pay for their training? So again, we're going to ask ourselves, does order of selection matter? In other words, does it matter the order in which these 10 people get picked? Is the first guy that gets picked, or the first person that gets picked, are they going to get something different than the second person or the third person? In this case, the answer is no. Everybody's getting the $1,500. So that means that we should use combinations. Okay, so we're going to check the combination rule. Now, the combination rule is, real quickly, n item, or from n items, we can pick combinations of r. And that would be equal to, the number of ways to do that is equal to n factorial over n minus r factorial. Now again, this looks just like the permutation formula, except we're also going to have down here on the bottom, we're going to multiply in an r factorial. Now, in this particular problem, again, you want to make sure you identify what n and r are. So that's n is equal to the 17 people, 17 employees, and r is going to be the 10 selected. Let's see if I can spell it. Okay, so we get this out of the 17 employees, the 10 that are selected make up R. Okay, so applying these values into the formula, we're going to have 17 items, and we're choosing 10 of them, and that's going to be 17 factorial divided by 17 minus 10 factorial times 10 factorial. Now 17 factorial on top, and on bottom, 17 minus 10 would be 7 factorial, 10 factorial. And as you can imagine, it's going to be a lot there to write out. Let's take a look at it. If we write it out the long way, that's going to be 17 times 16 times 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Let me catch my breath. On the bottom, 7 factorial would be 7 times 6 times 5, 4, 3, 2, and 1. And then 10 factorial would be 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. Whew. Okay, so starting to look at this now, you can see that I have this nice section 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and I also have that up here on top. So I am going to cancel all of those things out, leaving me on top with 17, 16, 15, 14, 13, 12, and 11, and on bottom 7 times 6, 5, 4, 3, 2, 1. At this point, you may choose to continue to cancel. I'm going to slide this down just a little bit and extend the screen out so we can see what we're working with. And I know my handwriting is a little messy here, but we can pick out a few things to eliminate. For example, 4 times 3 is equal to 12. So I'm just going to cancel out 4 times 3 and 12. Also, I have 7 times 2. Well, what does 7 times 2 make? It makes 14. So it cancels that out. You can cancel out 5 and make this 15 a 3. Different things you can do there. But I'm just going to stop it there and just take whatever's left over. Let's see if we can make a little bit more sense of it by cleaning it up. I'm left with on top 17, 16, 13. I left the 3 out. So you have to be careful when you start canceling out everything else, you don't overlook something. 17, 16, 3, 13, and 11. These are all the values that were left up here on top. On the bottom, what am I left with? Just that 6 and 1. So 6 times 1 is 6. So we can multiply out all of this stuff. And we have 17 times 16 times 3 times 13 times 11. And that gives us a very interesting number, 116688. And we're going to divide that by 6. Well, that simplifies down to 19,448. So that means that there were 19,448 ways for them to award these 10 different scholarships to these employees. So the answer to the question, how many different ways can the employees be selected to receive this bonus pay, would be 19,448 ways to do that, which is a lot. However, if the order mattered, we would have had even more. So keep that in mind. Combinations are still going to end up being a little bit lower than they would be if you had permutations in the problem. Let's take a look at just that and talk about how that works. Here's another example. There are 9 equally qualified students applying for a scholarship, of which only 5 are going to be selected to receive. If the scholarships are all equal in value, how many ways can the 5 scholarships be given? So again, we're going to ask ourselves, does order matter? In this case, the scholarships are all equal. Okay, so does the order of selection matter? The answer is no. So we will be doing a combination. So again, real quickly, the combination rule is n combination of r would be n factorial over n minus r factorial times r factorial. And as we do that in this case, n is the number of students that we're looking at overall, and that would be 9 students. And R is going to be the 5 scholarships that are selected, or the 5 students that are selected. Okay, so we'll go ahead and apply those values to the formula, and when we work that out, we have this, 9 combinations of 5, or excuse me, selecting 5 from 9 of combinations. That's going to be 9 factorial divided by 9 minus 5 factorial times 5 factorial. And real quickly, that's going to be 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. And on the bottom, we would have, this is going to be 4 factorial, so that would be 4 times 3 times 2 times 1. And of course, this is 5, so that's going to be 5 times 4 times 3 times 2 times 1. So as we look, we can see we have 5, 4, 3, 2, 1 and 5, 4, 3, 2, 1, and we will cancel those out. Over here, I also have 9, 8, 7 times 6, and 4 times 3 times 2 times 1. You can do a couple of different things. I'm going to take this 3 times 2 and cancel it out with the 6. You could also take the 4 and cancel the 8 out and make it a 2 if you wanted to do that. That's another method. But again, that's simplifying out as much as you can before you start getting your final answer. If we look real quickly, that would leave us with on top 9 times 2 times 7. And on the bottom, we would just have 1. So 9 times 2 times 7 is going to end up being 126. So we have 126 ways that the 5 recipients of this scholarship could be selected. Now, if we look in Part B, we can see a minor difference here. If the 5 scholarships are going to be valued at $5,000, $4,000, $3,000, $2,000, and $1,000, how many ways can the scholarships be awarded now? Again, the order in this is what we're going to be worried about. Does the order matter? And in this case, the order that you're selected does matter. So the answer to this question is yes. And the reason why is because we have a different value for every scholarship. So if you're picked first, you would get a $5,000 scholarship. If you're picked second, you'd get a $4,000, and so on. So the order that you're picked in is very important as to the amount of money that you'll receive. So we're going to use the permutation rule. And the permutation rule, once again, is this, n factorial divided by n minus r factorial. And there's nothing else down there on the bottom. So in this case, n is still the 9 students that applied for the scholarship, and r is still the 5 selected. But because the order matters, we're going to get a bigger number of options for the selection process. So let's look and see what this comes out to be. This would be 9 students, and we're selecting 5, so that would be 9 factorial over 9 minus 5 factorial. And we look at this, again, as 9, 8, 7, 6, 5, 4, 3, 2, and 1. We're going to divide that by 9 minus 5 factorial, which is 4 times 3, 2, and 1. Well, you can probably get the drift by now. 4, 3, 2, 1, and 4, 3, 2, 1 are going to cancel. So we're left with 9 times 8 times 7 times 6 and times 5. So as we multiply those out, we get 15,120 ways. So you can see, since the order matters more in this problem, or in this part of the problem, there are going to be far more ways for the selections to be made. And that is something we want to take into account and make sure we understand that the difference here is because the order of selection does make a difference in this problem. All right, one final example to look at, and it kind of ties in a little bit with probability. We're looking at a horse race, okay? We have several different horses running in a race. In fact, there's 10 horses here that we have running in a race. And the question is, how many different ways can the horses finish in first, second, and third place? Well, of course, in a race, the order in which you finish does matter. So we know that order matters. Okay, so that means that we're going to be using the permutation rule. And we can real quickly, I won't write up the formula, but we should be able to identify what n is and what r is. N is the 10 horses. Okay, and r we'll call the 3, we'll call them the winners, even though there's really only one winner, but we'll say first, second, and third all win prizes. So r is 3. So as we go to set this up, that's going to be 10 items, and we're going to choose 3 of those items, and the order matters, so we're doing a permutation. So that's going to be 10 factorial divided by 10 minus 3 factorial. And again, that's going to be 10 times 9, 8, 7, 6, 5, 4, 3, 2, and 1. And we're dividing that by 7 factorial, which is 7, 6, 5, 4, 3, 2, and 1. If anything else, these give you a lot of things to write out. So, but doing it out by hand, we can see we cancel out from 7 down, and that leaves us with 10 times 9 is equal to 10 times 9 times 8, which is 720 ways for these horses to finish first, second, and third. And of course, that's based on the fact that they would all be equal, and we were just kind of guessing at the ways they could finish. All right, so that said, we're going to try and guess the order that these horses are going to finish as a contest, see if we can win something. What is the probability of guessing the top 3 finishers in order? Okay, so basically there's 720 ways for these horses all to finish. What is the probability that I guess that? Well, remember, probability is equal to the number of wanted outcomes divided by the number of possible outcomes. Okay, so in this case, the number of wanted outcomes, well, the only outcome we want is the outcome that we're going to guess, all 3 of those finishers. So that would be, there's only 1 of those. And the total number of possible outcomes we just decided was 720. So the probability would be equal to, and we guess right, the probability we guess right would be equal to 1 over 720. And of course, that's not a very good chance. If we looked at it as a percentage, that would end up being 0.14%, somewhere around there. That's 0.0014 somewhere as an estimate. And that's not very good. So probably not a great idea for you to try and guess them if you were going to have to spend a lot of money to get a guess. But at any rate, that's the probability that you could possibly guess right out of that. Now, that's a way that we would apply the permutation rule to computing a probability. We figure out the number of possible outcomes, like we did in this first part, and then we look and see how many of those possible outcomes would be in our favor. And in this case, there was only 1 in our favor, and 1 out of 720 is not a very good chance. Hopefully we cleared up some of your questions about permutations and combinations. Remember, these are word problems that you're going to encounter quite frequently when dealing with probabilities. The best idea to get used to working with these is practice them. Once you read several of them and you learn what you're looking for, it really makes it a lot simpler. Just remember, you want to do this, and good luck with everything. If you have any questions in class, please feel free to ask, and I'll be coming around to help you soon enough, I'm sure.